Let's look a bit further at what's happening here so we can make sure we're on the same page in terms of the notion of compounding of interest. It's really important as we go forward. Let's say we start with that $10,000 that we have invested. And let's say you put that money into a bank account and it's supposed to earn 10% compounded annually, once a year. You may watch that statement throughout the year and wonder where the interest is. You contact the bank, let's say, and say, hey, where's my money? I know I'm supposed to be earning interest at 10% throughout the year. And they would have to at some point explain, yes, it's compounded annually. What does that mean? That means that once a year, interest is calculated on this sum and interest is then added to your account balance. And then what's really important about understanding compounding is then that the sum of that original balance plus the interest earns interest in the subsequent period. And so let's look at that. During the first year here, then we're going to earn interest at a rate of 10%. Well, if you recall how interest is calculated, we use this formula here. I equals P times R times T. Principal times rate times time. And so in this first year, we have a balance of $10,000 that's invested. The interest rate, or rate of return, is 10%. And since we're calculating interest for one full year, then T here is 1. That 10% is annual, and so this is the number of years. And that means that interest earned, 10% of $10,000, is $1,000. Probably do a little bit better than that, but there's $1,000. So here's what happens throughout the year. You watch your balance, nothing, 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 until finally, at the end of the year, $1,000 is added to your balance. And so now, from the start of the second year throughout that year, you have $11,000 that's earning interest for you. And so again, you watch your balance, nothing happens, but at the end of year 2, the bank will add the interest on that amount. But of course, now you've got $11,000 working for you. And so if we calculate the interest on $11,000 using the same process, $11,000 times 10% times 1 is equal to $1,100. So there's your interest. You can see why I picked 10% because it's pretty easy relatively easy, to do this in your head. So 10% of 11,000 is 1,100, and that means we've now got a balance starting at beginning of year 3 of 12,100. If we continue this process, we see that in year 3 the interest is 1210. That gives us 13,310. In year 4, we earn interest of 1,331. That gives us 14,641 as the balance for that period. And I know I'm getting a little askew here, but hopefully you can still follow. And 1,641.10 is the interest for that last period. That means that our balance then is, if you add that up, $16,105.10. In other words, it's that balance that we found when we did the problem using, using the mathematical formula. So notice here the notion of compounding is interest earned on interest. See how interest in the first period was $1,000. But now interest in the next period is $1,100. That $100 of additional interest earned in that second period is because we have added the interest earned in the first period to that. And notice the interest earned in every period then is going to increase. Here it was 100, there it was 210, there it's 331, there it's 464. And so you can see it's getting larger and larger in an exponential sense. In other words, it really is sort of a snowballing process. If you understand the notion of snowballs, you know that the snowball gets bigger as it rolls down the hill, not just because it's rolling further, but because the surface of the snowball is actually getting larger, and so more snow is sticking to it for any given distance that it rolls than it did before. And so that's important in understanding time value of money. So it's a good illustration. Hopefully you can develop something of a gut feel then, a better feel for actually what's happening here, because the illustration of the snowball is actually a pretty good representation of what's happening here mathematically. Well, let's go to one more, the next illustration. I guess I better turn around here. I'm getting wrapped up in the cord. This is the first time, of course, I've tried to do this. We'd like to have a wireless mic, and maybe here in the College of Business we can do a bit more of this and get a bit more better technology in the future to make this a better experience for you guys. Well, let's go back to our original formula, the future value of $1. The future value at the end of end periods is figured by or determined by applying this formula here. And so we saw that if I is equal to 10% and n is equal to 5, we got 16, 105, 10. But what happens if we increase the frequency of compounding, all else the same? In other words, the annual interest rate is the same. We're just talking about compounding more frequently. Well, let's say, I think it's on the snowball sheet there, it says, what if we have quarterly compounding instead of annual compounding? Well, what changes here? Well, our definition of I, remember, is the periodic rate, the annual rate divided by the number of times compounding takes place each year. Well, 10% is the annual rate, but of course we have quarterly compounding, that's 4 times a year. And so that's 2.5%. N is the total number of times compounding takes place over the investment term. So if it's compounded now 4 times a year for 5 years, N is equal to 20. And so we need now to calculate that the value of this factor here. And that is 1.025. And this cheap calculator that I've got doesn't give me that value. I've got to use my calculator on the phone here. Neither does that one. I guess I've got to use my financial, well, a better calculator anyway. There we go. Here's my BA2 Plus on my phone. By the way, if you get it for your iPad, you can add it to your phone, of course, for no extra charge. But I'm going to use the way that you would on a regular calculator, and that is 1.025. My fingers are too big for this thing. Raised to the 20th power equals 1.6386. 1.6386. It might go out a little bit further. I've got my calculator set for 4 decimal places. But anyway, there you see $16,386. And you would note, of course, the more frequent compounding adds to the future value. Before it was 16,105, I believe. So it's added about, what, $281, a little over $280 to the future value just for more frequent compounding. Okay, what's happening there is you've got interest, instead of waiting to the end of the first year to add some interest, you're waiting only 3 months, and then you're calculating that interest, 2.5% to that point, adding it to the balance, and then that sum earns interest for the next quarter. Then you add the interest for that second quarter, and so on. So really, with more frequent compounding, the interest rate is the same, the length of the investment is the same, but you've got your money that's going to work for you faster with more frequent compounding. And if we were to change this to monthly compounding, for instance, then of course we would simply go back and say, okay, 10%, the annual rate, divided by the number of times compounding takes place each year, which of course would be 12. And so we get sort of an ugly number there. I think it's a 0.0833 there. And N in this case, if it's 12 times a year for 5 years, N would be 60. Okay, so if we solve for that, and we know that it's going to be a greater amount even than this, and so I won't show it here, but let me calculate that. The 1.00833, that's what that is. Sorry, I've got one. Let me make sure I've got that right. 0.10 divided by 12. 0.8403. Yeah, 0.0088403. No, that's right, 0.0083. Okay. That's going to be our interest rate, so it's 1.0083 raised to the 60th power equals 1.642. So that factor then is 1.642, which means that $10,000 would become $16,420, so a bit higher than this amount here. Anyway, hope that last part wasn't confusing for you. If you need to go back through and just prove the numbers to yourself, of course, I encourage you to do that. There's no way really to become more comfortable with these formulas and with the applications than by simply using them. Let me mention one more thing that is relevant here, and that is that given, notice we have 4 variables, and given any 3 variables, we can solve for the 4th one. In this particular case, for instance, we had the present value, n and I, and we solved for future value. But you could, in fact, solve, if you had present value and future value, you could solve for I or solve for n. Okay? As long as you've got 3 of those variables, you can always solve for the 4th one. But I tell you what, that's going to be hard to do mathematically. Maybe not initially, but once you get to these formulas that deal with the future value and the present value of annuities, you don't want to be solving for n and I in those. It's going to become too hairy. You're going to have to use some calculus there, and life's too short. I'm not doing that. But we will use the financial calculator. So let me turn your attention to the usable form of this model, because this is where we're going to jump off. From here on out, we're not going to be using the mathematical models so much. We're going to be using the usable form and using the TIBA2+ calculator to solve problems. Well, notice the usable form of this model looks like this. The future value is PV, and then N equals and I equals. I think that's the order in which they have them there. It doesn't matter whether these are reversed. We're not, again, using or applying the mathematical model here. I like the usable form because what it does is it retains the appearance of the mathematical model. So it should assist you in solving more complex problems, sort of using the building blocks to put together solutions for more involved or real-world problems. But notice we've got these 4 variables, and so right here, in order to solve this problem, I have to identify PV, N, and I to solve for FV. But also, since I'm having the calculator do the hard work, I could identify PV, FV, and N and solve for I. Or FV, N, and I and solve for PV. I've got all kinds of variations here. So the TIBA2+ calculator has a row of keys. Tell you what, let me stop this video and I'll go into the calculator next.